Right. Well, I'll give it a couple of minutes just for people who are showing up later. Teleport right at the time of, so I'll just start in a couple of minutes. Is that Venus de Milo that's at the back of the room a mesh object? I'm guessing it must be. Did mess around with sculpties a fair bit once upon a time, and I used Blender to make sculpties. Yes, when in doubt, relog always seems to be the thing. All right, well, I'll get started here. So welcome everybody to the Science Circle presentation. I guess this is the first one of the year. And given that the year has only been around for 2 days, that's probably not too hard to do. So welcome to 2016, everybody. That just kind of boggles me because the number 2016 sounds like the far future to me. The whole 21st century thing. I mean, I remember when 2001 was the far future, and we were going to, be on the moon and then have an expedition that we sent to Europa and all of that kind of thing. But whatever. Now we're in the real world and we have to deal with it. So I'm giving a talk about neutrino oscillations. The reason I'm giving this talk is that that was the topic that got the Physics Nobel Prize in 2015. And so that makes it a hot topic right now, although really it was a really hot topic about 15 years ago or so when the discoveries were made. But as you know, they don't give Nobel Prizes the year after the discovery. They wait and make sure that it sticks. But this certainly was a very important discovery, and I'll try and explain why. But if you're not a physicist and you don't know a lot about this, and you see the title, it immediately begs two questions. The first question it begs is, what is a neutrino? And the second is, what does it mean for a neutrino to oscillate? Oscillation just means some sort of wiggler going back and forth. But the oscillation that neutrinos do is not actually a vibration type oscillation. It's a much more abstract sort of thing. So I will attempt to explain what all of that means. So that's the talk for today. So welcome everybody. I am Rob Knop. I actually finally changed my display name so that, yes, Vic makes an important point. You have to be alive to get the Nobel Prize. And so, especially if you're old, sometimes people who probably deserved it don't get it because they die before it's time. I finally actually changed my display name so it has Rob Knop. You can see that. But I am the same Prospero Frobos that I have always been, which was always the same Rob Knop that I always was, unless you subscribe to theories like the atomic theory, which suggests that all of our atoms get replaced over the course of however many years it is, and then I'm not the same person at all. I just happen to think I am because of the illusion of consciousness continuity. But that's a whole different topic that I'm not going to even touch. So here we are today. I am a professor at Westminster College, which is a small liberal arts college in western Pennsylvania. If you know anybody who lives near Pittsburgh and has students who are interested in going to a small place where they get lots of personal attention, tell them to check us out. That was the advertisement. So, neutrino oscillation. So I'm going to start by talking about what the heck a neutrino is. Yes, I just mentioned these are the two guys who actually got the Nobel Prize. And this is one of those Nobel Prizes, sort of like the one that I was vaguely associated with a few years ago, which was for the discovery of the accelerating universe, was given to 3 people. But really there were something like, with the accelerating universe, something like 100 people involved. And there have been other prizes. For instance, just last year, the Breakthrough Prize went to the entire team, which I shared in that, which was pretty exciting. So I'm guessing there will eventually, if it hasn't already happened, I think in fact it did happen this year, the Breakthrough Prize went to the Neutrino Oscillations people, and everybody on the team shared it, and there were several hundred people involved. But these were the team leaders, and the Nobel Prize is limited to only 3 people. And there were 2 primary experiments. One was the Kamiokande experiment in Japan, and that's what the guy on the left, I'm probably going to say his name wrong, but I'll try. Takaki Kajita, I think is how you say it. And then the second one was an observatory in Canada, the Sudbury Neutrino Observatory, and that's Arthur B. MacDonald. That name I am more culturally disposed to be able to say well. So anyway, those are the guys who won the Nobel Prize. But what I'm going to try and talk about today really is the science behind all of it. So, well, no neutrinos here yet. The whole story of neutrinos begins with the story of nuclear decay, which is something that was discovered 100-ish years ago now. Marie Curie, of course, is one of the more famous Nobel Prize winners associated with these sorts of things. But there are a lot of people working on this back in the day. And it was noticed, radioactivity was noticed, that there were certain different kinds of things that would happen when radioactive decay happened, that different detectors and different sorts of characteristics were seen. And early on, they didn't even know what the things were. Nowadays, we do know what the things are that are coming out of the nuclei, but early on, they just sort of categorized them based on, oh, these are different from the other ones. They called it alpha, beta, and gamma, the three types of decay that they generally saw. Nowadays, we know that alpha decay, what happens is that you start with a big old nucleus, and the big old nucleus is unstable, and the result is it kicks out a alpha particle. We actually call it an alpha particle, but you might more properly know it as a helium nucleus. So helium atoms have 2 protons, 2 neutrons, and 2 electrons. Well, so if a nucleus is unstable, sometimes it can make itself more stable by kicking out 2 protons and 2 neutrons, and then what's left behind is a slightly smaller nucleus that might be either stable or less unstable, and then this alpha particle goes flying away. But there are other ways nuclei can decay, and another one is by what's called beta decay, and there's actually 2 different versions of beta decay, but in one of them you have a nucleus that's unstable. It kicks out an electron. Now, electrons have an electric charge of -1, and that's in units of, wait for it, the charge on the electron, really the absolute value of the charge on the electron. So because it has a charge of -1 and electric charge is conserved, that means after the nucleus has kicked out the electron, its electric charge must have gone up by 1. So one way you can think about this is that one of the neutrons turns into a proton, and it kicks out an electron to balance the electric charge, and this is called beta decay. And beta decay is the one we're going to be talking about a little bit later. And then finally, there's gamma decay. Those of you who know about atomic orbitals may know that atomic orbitals are sort of useful for 2 things. If you're a chemist, you mostly think about them in terms of how do you build up the ground state atoms and therefore the periodic table. But also, depending on what kind of chemist you are, or if you're a physicist, you're interested in the fact that even if the orbitals don't have electrons in them, they're still there. And if you give energy to an atom, you can kick an electron into a higher orbital, and then when it falls back down, it'll emit a photon, which is often an ultraviolet, infrared, or visible photon. And we've seen those through spectroscopy, and that's how we identify lots of atoms, both in space and on the ground. So that happens in atoms. Well, it turns out that as there are orbitals for atom, there are also nuclear states that are sort of like orbitals, and in fact are called that sometimes, depending on which nuclear model you're using. It's much more complicated with the nuclei than it is with the electrons in the atoms, and the electrons in the atoms are already pretty complicated. But if you have a bunch of nucleons, it turns out that sometimes, and one prosaic way of thinking about it is they can rearrange themselves a little. A more quantum way is saying they drop down to a lower energy state. No protons or neutrons turn into anything else. There's still just as many protons, just as many neutrons, but they go to a lower energy state, and the energy that they lost is released in the form of a gamma ray, as it's called. But nowadays that we know, a gamma ray is just a photon, a very high energy photon in what we call the gamma ray region of the spectrum. So it's the same thing as light, fundamentally. It's just each little particle of it, each photon, is much higher energy than what we think of as visible light. So these are the 3 ways that nuclei generally decay: alpha, beta, and gamma decay. And they were all studied a lot in the first half of the 20th century. Well, oh yes, here I am talking about the atoms. I should have showed you that slide. So these last 2 slides are all about the atoms and how stuff comes out, but I can kind of skip them now that I already talked about it. So nuclear gamma decay works like the atoms. Actually, you know what? I just do want to point out, even though I already said it, that there are specific orbitals that are available to atoms. So if, say, a hydrogen atom it has an electron in this state, which might have happened, say, because there was a free electron that got captured, not in the ground state. And then as it jumps down from one state to the next state, these states, according to the laws of quantum mechanics, are at specific energies. And therefore, when you go from this state to this state, the amount of energy lost is equal to the difference in energies. So the photon that comes out has to have exactly the right amount of energy, and that corresponds to a certain wavelength or frequency or color. And like, for example, H alpha, as it's called, one of the most famous hydrogen frequencies, corresponds to the third level to the second level transition in hydrogen. So there's just one electron falling from excited states down to the ground state. This would be what's called a Lyman alpha photon, which is in the ultraviolet. Right, and yeah, and so here we see these as what we call lines. This would just be a spectrum if there was, say, an emission tube, like a neon light, as you call them. But neon lights have neon in them, but sometimes they have other elements to make them colors other than the pinkish that you get from neon. You can have a hydrogen vapor tube where you excite it and you get electrons jumping up and down through the hydrogen states, and you see light at very specific wavelengths, including this H alpha wavelength here. If you were to make a plot of intensity versus wavelength, what you would see, wavelength along the horizontal axis is nothing, 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 oh, a spike. Nothing, nothing, spike, nothing, 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 spike. That's what you'd see in the plot. And that is similar to what you see when you look at the gamma ray decay spectrum for nuclei. So this is an example of a nucleus. I don't remember which nucleus this is anymore. I think it's, oh no, it's a few different ones. You can see the nuclei are labeled up here, and this is where I got this picture from. But this is just a gamma decay spectrum. There is a continuum, so there's some background gamma rays there for one reason or another that just have to do with the whole way the environment was set up. But you see there's these very specific wavelengths. Now here we have energy, but a given energy of a photon corresponds to a given wavelength of a photon. So there's very specific, let's just say energies, wavelengths can be either way, very specific energies which lots of photons come out of. And each one of these energies corresponds to a specific transition between two different states of the nucleus over here. And so this is really what you expect to see because of quantum mechanics. What quantum means is sort of numbered, quantized, just means that things come in specific steps as opposed to a continuum where things are just sort of smooth all the way through. So there's very specific individual wavelengths that things come out at that correspond to the energy that is lost by the nucleus when the thing is left. So there you go. So that's what happens with with gamma decay. Beta decay is different. When an electron is kicked out, you do not see specific wavelengths at all. What you see is entirely a continuum spectrum. And this is a paper from 1935. So this is back when they were still trying to figure out what the heck was going on with this. It's a continuous spectrum, which you might say, well, okay, that's no big deal. Light bulbs put out a continuous spectrum. The sun, if you don't look too closely, puts out a continuous spectrum. Why do you care? Well, the reason we care is this is stuff coming from single nuclei. A single nucleus, we already know from the gamma ray, has quantized nuclear states from looking at the gamma spectrum. But if it does have quantized nuclear states, why is it that you can kick out electrons with different amounts of energy? That is surprising and sort of inconsistent with what you get from the gamma rays. So that was a problem. But there was an even bigger problem. So there are three, all right, these are not the three guiding principles of physics. These are three of the guiding principles of physics. But these are really important ones. In some ways, these principles of physics are more important than things like F equals ma, if you've heard of that, which is Newton's laws for motion. These three guiding principles of physics seem to show up in every single physical theory that we have. Every physical theory has some version that is recognizably these theories. Now, there's some, like general relativity. When you talk about conservation of energy and general relativity, it becomes kind of complicated. But there is certainly a version of it there. And certainly when you're talking about little localized areas, conservation of energy is a thing that if you have, say, you draw a box around a bunch of stuff, if you can measure the amount of energy going out of the box, say, emitted by particles, that will be the same as the change of energy of the stuff in the box. That's what conservation of energy really says. And there's conservation of momentum and conservation of angular momentum. Well, the beta decay spectrums, when you really measured the beta rays coming out, and beta rays was just the electrons coming out, and you measured their energies, it was looking like energy was not conserved. We had this real problem. Energy seemed not to be conserved in these. If you measured the energy of the nucleus before and after, and of the electron that came out, it was not adding up right. And so in the 1930s, Niels Bohr, who's a really famous physicist, was suggesting maybe conservation of energy isn't right. Yeah, it's a no-no. Well, really, why is it a no-no? It's a no-no because everything in physics seems to have obeyed conservation of energy. Now, of course, in science, we always have to be ready to throw out our most cherished postulates if there is really strong evidence showing that they no longer work. And we have done this. For example, with the advent of relativity, we had always assumed it was a postulate that we didn't even really say because it seemed obvious, and it still kind of seems obvious to everyone, so much so that it gets hard to me to explain to you why you think this is obvious, because you don't even seem to think there's something to explain, is that time is universal and the same for everybody. It's something that just seems kind of how it is. That if you synchronize your watches are synchronized. If your watches are perfect, then they're good. Well, we had to throw out that notion with the advent of special relativity, and the data showed us that special relativity was right and the notion of absolute time wasn't. So conservation of energy, we really hesitate to throw out because there's lots of reasons to think it should always be true, and because everything that all our physical theories that have been tested and that have worked up to now have this as a feature. So conservation of energy is one of those things you need really, really strong evidence to abandon. They were considering that back in the 1930s because of the nuclear decay problem. So how do you get around this? If you don't want to get rid of one of these cherished physical principles like conservation of energy, you have to come up with some alternate explanation, and ideally you then want to be able to test that explanation versus getting rid of conservation of energy in order to decide which explanation is right. The litmus test in science is, can you test it versus experiment, test it against the real world. And I'm not going to talk about a recent conference having to do with string theory. That's a topic for a whole different day. Well, so Pauli proposed, and that's what Vic just said, added something on one side of the particle equation. Pauli proposed that there were these things that he called neutrinos. Actually, he originally suggested they be called neutrons because the thing that we call a neutron today hadn't yet been discovered. And when the neutron was discovered, and it clearly wasn't Pauli's particle, they started calling Pauli's particle the neutrino. So Pauli proposed, well, maybe there's these really lightweight, extremely hard to observe particles that are coming out, and that's where all the extra energy is going. And I love this quote. This is from a speech that Pauli gave at a conference that I found the transcript of. Here's where I found the transcript. That's the reference down there. But Pauli said, I admit that my expedient may seem rather improbable from the first, because if neutrinos existed, they would have been discovered long since. Nevertheless, nothing ventured, nothing gained. We should therefore be seriously discussing every path to salvation. And notice the language, salvation, meaning keeping us from having to throw out conservation of energy. In the same talk, Pauli also said that he was about to do something that no scientist should do, which is propose the existence of a particle we almost certainly will never be able to detect. At the time, he thought, wow, this is going to be too hard to detect. We have stuff like that today. We have dark matter. We're not really sure what it is. We have some ideas of how to detect it, but we still don't know what dark matter is. Several years ago, I gave a talk in Second Life where I said that I hoped that by, and I didn't give a year on it, but I'll go ahead and say by 2016, the Large Hadronic Collider would have discovered supersymmetry, and that the lightest supersymmetric particle would have fit what would be dark matter. Well, the Large Hadronic Collider has not discovered supersymmetry, has set some really hard limits on this, so we still don't know what dark matter particles are, but we still think that there's something. But with things like that, there are some things that we think exist because we see secondary effects of it that we may never be able to detect directly. And Pauli thought he was proposing that and was really hesitant to propose that. But propose it he did, and it turned out that he was a little too pessimistic, because nowadays we detect neutrinos all the time. So his proposal was correct, and not only was it correct, but it turns out we were able to detect the particles that he was predicting. So here's one of the very early experiments that was proposed and even approved, but unfortunately never went through. Let's see. Interacting Fermi. Oh, yes. So that's talking about the neutron. Yes. Anyway, the proposal was that you have a little tower here, and you put, yes, a nuclear bomb at the top of it. Why? Because there's a whole lot of nuclear reactions. Now, there's even more in the sun, but the sun's pretty far away. So you have a whole lot of nuclear reactions, and then you have a suspended detector that is protected from being exploded by the nuclear explosion, by all sorts of stuff in the way here. But on the other hand, neutrinos, because we haven't been able to detect them, the idea was neutrinos go through matter really easily. Then your neutrino detector down here would detect a tiny, tiny fraction of the neutrinos, but there'd be so many of them that it would detect some. This was proposed and approved, and I generally approve of anything that involves massive explosions for science. And so I'm kind of sad that they never actually blew these nuclear bombs off, and so I'm going to build one in my backyard and do it. So I'm sorry, anyone who lives in Pennsylvania or Ohio, but you know, it needs to be done. No, I'm not really going to do it. I'm probably on a terrorist watch list now that I said that. So the first real discovery of the neutrino actually happened in 1956 and what they did is they discovered neutrinos coming from a nuclear reactor. So we already built nuclear reactors, and we already were producing neutrinos in bulk on Earth. We just didn't really know it yet. And so near the Savannah River in North Carolina, there was a nuclear reactor, and they built an underground detector. And this is just sort of a little it's kind of hard to read in this, but there's a little thing that describes how the reaction goes. So, and it's actually an anti-neutrino. I'll get into those details later. Coming in, interacted with stuff, and there were a bunch of secondary interactions, and then you detect the photons that come out as a result of it. So the neutrinos were discovered 26 years after they were hypothesized, which sounds like a long time, but it's been longer for dark matter. So, you know, we're suffering nowadays. But yes, so Pauli proposed this thing that yes, it was the electron anti-neutrino, but I'm sort of talking about neutrinos and anti-neutrinos as if they were the same thing. So Pauli proposed these particles in 1930, and at the time thought this is something that there's no hope of us ever being able to identify. And 26 years later, we found them. The other thing is that the physics community, by the time they were discovered, wasn't like, oh my God, they're real. It's like, oh, phew, they're real. Everyone sort of accepted that they were right at that point, and we're just waiting for the confirmation to come in. So it wasn't necessarily a surprise. The explanation worked so well that people really hoped that it was going to pan out, and sure enough, it did. And nowadays, neutrinos are a very standard part of the standard model of particle physics. Now, I also need to talk about unfortunately, I don't have an extra reading handout, but if Vic has already posted at least one link, and what I will do, the slide here will be available. I think anybody can copy them, but if not, let me know and I'll make it so anyone can copy them at the end. Anyway, we also need to talk about neutrino astronomy. So far, 2 individual objects have been detected. There has also been detected some neutrino backgrounds at very high energy, but 2 individual objects have been detected in neutrinos. One is the Sun. The other is supernova 1987A, which is the closest supernova that we've had since we've been detecting neutrinos. They were both detected, well, the solar neutrinos are detected by lots of things. 1987A was detected by the Kamiokande detector in Japan, which is related to the same one that was used to discover neutrino oscillations. So neutrinos were detected from the Sun. They were predicted from the Sun because of all the nuclear reactions in the Sun. That in fact, if you look in the Sun, now I have hidden all kinds of gory details behind this little explosion-looking thing, but hiding all the gory details, the way fusion generally works in the Sun, there's a couple different paths that things go through, but the basic idea is you start with 4 protons that are all zipping around at the center of the Sun. Now, most of the universe, if you talk about the stuff that's made out of protons and neutrons, which all atoms are, well, protons, neutrons, and electrons, but electrons are small, so I often forget them. If you look at normal matter made out of that stuff, in the universe, almost all of it is hydrogen. 90% of it, by number, is hydrogen, and most of the remaining 10% is helium. Earth is a very special place because the element abundances are very different here. They collected together in the early solar system. All the heavy stuff kind of collected into planets, and then we get to live on one of them because, I don't know, we paid the rent or something. But in the Sun is a big ball of mostly hydrogen. So there's lots of hydrogen at the core. The hydrogen, it's hot enough, meaning the particles are moving fast enough. So really what temperature means is how fast are particles moving randomly around. So the particles are randomly around moving fast enough, and it's dense enough that they run into each other often enough that fusion can happen. And again, there's a complicated set of things that happens, but these 4 hydrogens come together, At the end, you get a helium nucleus. So this is the fusion of hydrogen up to helium. Well, notice that these 4 hydrogens have a total electric charge of +4 in electron units. The helium nucleus only has +2. Where'd the other +2 go? Well, 2 positrons. So a positron is an antimatter particle that is the antimatter particle partner of the electron. So it's like a positive version of the electron. 2 positrons get produced, and there's also a whole bunch of electrons tooling around at the center of the sun. So what will happen is the positrons will very quickly find electrons. The 2 will come together and annihilate, matter-antimatter annihilation, and produce energy in the form of gamma rays. But also, so that's what happens to those guys. The helium just sort of hangs out at the center of the sun and builds up. There's also 2 electron neutrinos produced, and this comes out of another conservation law that's very important in physics. That's not energy momentum or angular momentum, but something much more sort of abstract called lepton number conservation. So the idea is that the total number of electrons plus electron neutrinos has to stay the same. An antiparticle counts as a -1. So these 2 things count as -2 electrons. There were no electrons over here, so to balance it out, we have to have things that count as +2 electrons, and the 2 electron neutrinos take care of that. These neutrinos, however, almost never interact with matter. That's one of the characteristics of a neutrino, is it almost never interacts with matter. So they just flow freely out of the sun, even though the sun is this big, huge, dense ball of gas that light can't get through, that gamma rays can't get through. Neutrinos, whoop, just go right through it. Isaac Asimov had a quote in a popular science article he wrote something like 30 years ago, where he said, to a neutrino, matter is just a high grade of vacuum, which is a good way of saying it. One interesting thing is that if you look at your thumb, and the reason I say your thumb is because it's about a square centimeter, and I forget the number. I always calculate this number, and then I always forget it. But something like 100 billion neutrinos are going through your thumb every second, and you don't feel it because they just go right through your thumb and don't interact with anything. Those neutrinos are from the sun. So there's huge numbers of solar neutrinos produced in this nuclear reaction at all times. Well, okay, so this over here, I think this is Ray Davis and this is John Bacall. Ray Davis is also a Nobel Prize winner, which he got the Nobel Prize for discovering solar neutrinos. At the Homestake Mine in 1964, these 2 guys and a bunch of other people discovered neutrinos coming from the sun. Now, their roles were a little different. Ray Davis was really the experimentalist who got this whole thing working and made it all go. John Bacall was a theorist, still is actually, nuclear theorist, who did the calculations telling us how many neutrinos should we expect from the sun. And so these are based on our understanding of nuclear physics, which we understand really well because we've done it in lots of reactors and labs on the Earth, together with our understanding of stellar structure, which is based on the hydrodynamics of the sun and how it all collapses together. What is the rate of fusion we get at the center of different types of fusion? We also know the rate of fusion because the luminosity of the sun, all that energy ultimately comes from fusion. Put all those things together, and John Bacall can predict, as lots of people can do this, but John Bacall was the guy who sort of led it in the early days, predicts how many neutrinos we ought to be seeing from the sun at energies that could be detected. And the way this worked is they had a big old tank of basically cleaning fluid. So it had lots of chlorine in it. The tank was full of chlorine, but had no argon in it. So argon is a noble gas, doesn't interact with stuff. You just leave it running for a few weeks, and then you filter it out and see how much argon is in it now. And the reason there would be argon is that if a neutrino of the right energy came in and hit one of the chlorine, it would go through this reaction where the neutrino would hit, the chlorine would turn into an argon nucleus, and then an electron would get kicked out. So they weren't even detecting the electrons. All they were doing was just measuring how much argon came out. And from that, they could figure out how many neutrinos interacted with this big tank, and knowing how likely a neutrino is to interact with chlorine, which is not very likely at all, right? Remember, all those neutrinos going through your thumb do nothing to it. So it takes an ungodly number of neutrinos going through this chlorine tank before, oh, thank you, there it is, if you want to figure out the right number. And then maybe somebody can tell me if it really is 10 billion or whatever I just made up off the top of my head. It's a huge number. That's all I remember. So, anyway, so some tiny fraction of the neutrinos going into this chlorine tank make argon, and you measure it later, And excellent, we have detected neutrinos from the sun. This is important for a few reasons. One, it confirms what we know about neutrinos. Two, it confirms what everybody pretty much accepted by then, is that it is in fact nuclear fusion that powers the sun. This is classic science story, right? We have this model, nuclear fusion powers the sun. It gives us enough energy to give the light we see from the sun. It works way better than any other idea anybody has for how the sun could be powered. Okay, we think it's right. But if you're going to be Karl Popper, you say, well, you have to have some sort of falsifiable prediction that somebody can test from your theory that we haven't tested yet. You can't just explain stuff we already knew better than anything else explains it. That's nice. That suggests your theory might be right. But to really test your theory, you have to make some kind of, oh, look, I wasn't too far wrong when I said 10 billion. You have to come up with some prediction that you can test. And well, the prediction was there should be neutrinos coming out because nuclear fusion produces neutrinos. And yay, we found them. Nuclear fusion seems to work. There was a little problem though. And that problem was we were only seeing about a third as many neutrinos as we ought to see. And so this was a case that's like, we're seeing neutrinos, but there aren't enough. And this was a real problem for a real long time. It was called the solar neutrino problem, in fact. Calculations, and there's a couple of reasons. All right, so in the broadest sense, when a calculation doesn't match experiment, there's three general possibilities. One, you haven't done your calculation right, either just because you forgot to carry the 2 or something stupid like that, but more likely because some of your input parameters you hadn't estimated right or something like that. Number 2, there's something about your experiment that's wrong. That can happen, right? Data can be wrong. That sounds like sacrilege, but it's very true. And a classic example of that is, you may remember a couple years ago, there was this possible discovery that neutrinos were going faster than light. In fact, they weren't. And they figured out much later, well, months later, the people doing the experiment figured out, they had looked and looked and looked and couldn't find this, but eventually figured out that the problem was a cable that was not tight enough was introducing a tiny, tiny time lag in their measurements that led to a they sort of misestimated what time they were really getting from their experiment. So experiments can be wrong because there's some sort of systematic error or something going on in your experiment that you didn't do right or you didn't understand properly. So that can happen too. And that's what, in fact, that right there is the number one thing that makes experimental science hard, is finding all the little things going on that get in the way of the measurement you're really trying to do. So that's those two things. And then the third thing is that there is something new that nobody has thought of. That is always a possibility too, and that's the most exciting possibility. It's also the one that's least often the right answer. Well, so okay, let's say, so they checked their things and the experiments were good, and other experiments were done that confirmed that there was a deficit, that only a third as many neutrinos were coming from the sun as there should have been. That was confirmed by multiple different independent experiments, so we believe the data now. Lots of people worked on the calculations, checked the calculations. We believed the calculations. You could not twiddle the parameters within plausible possibility. Oh, hello. Person just dropped on me. You could not twiddle the parameters within plausible. Oh, it was Jess. Hi, Jess. You could not twiddle the parameters within plausible ranges and get anything near the number of neutrinos we were detecting. So we think the calculations were good. So we're now down to the point of it probably has to be new physics. And so let's talk about new physics in the broadest sense. One, something is weird about the sun. Our models of stellar structure, there's something really surprising about them. Or two, it could be something as weird about neutrinos. And so in the latter decades of the 20th century, experiments started being designed trying to test the idea that something was weird about neutrinos. There was an idea for what could be weird about neutrinos, and that idea was neutrino oscillations, and I'll next talk about what all that means. And what I show here is just one of the experiments, and this is the Sudbury Neutrino Observatory. Sudbury is a mine in Canada where they eventually replaced it with this gigantic tank of heavy water designed to detect neutrinos. This is one of the two experiments that got the Nobel Prize for the discovery of neutrino oscillations. Well, okay, so to talk about neutrino oscillations, I need to talk a little bit about the standard model of particle physics. Neutrinos come in what we call flavors. Now, we have this problem in physics that we use words to mean things that don't mean the same as what they mean in real life. So flavor is one of them. unfortunately. And there's lots of cases like this where it's just sort of an analogy. There's something different about these neutrinos. What's different about them? Well, these quantum properties, blah, blah, blah. Well, what are we going to call them? I don't know. They're different flavors. That sounds good. Let's call them flavors. All right, good. We're done. We also, if you know about the strong force, talk about red, green, and blue color charge. There is nothing red in terms of what it looks like to your eye about the red color charge in the strong force. It's just a thing that has three different bases, three different sort of base values, which is very much the way most of the ways we put together color are. Like, think about RGB monitors, if you know what that is. If you've ever played with imaging programs, you can see the red, green, and blue amount of color. So it's just something where there's three different versions of it. So flavor doesn't really mean that somebody is eating this and saying, nom, 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 you has a flavor. There's none of that going on. It's just a way of saying there's three different sort of kinds of neutrinos. So we're going to use flavor to talk about different kinds of neutrinos. So right here we summarize almost all of the known particles of the standard model of particle physics. There is one left out, which is the Higgs boson, which is a standard part of the model and has now been discovered. So add a little square somewhere and call it Higgs boson. But for all the rest, these are all the most fundamental particles of the standard model of particle physics, except that they also have antiparticles to go with them. The ones that you deal with every day are this one, the electron. You've all probably heard of that one. This little thing over on the left, that tells you the charge on the electron. So the electron is the stuff that makes chemistry go. There's electrons in all the atoms. Notice there's no proton or neutron on here. Protons and neutrons are made out of these two guys called the up and the down quark. So the up and the down quark are sort of paired. They're in what's called the first generation. Again, these generations have nothing to do with genealogy, and they're just another way of describing the categories we've put things into. So the first generation, or the first column, we should say, of particles includes the up and down quark, and two ups and a down make a proton, two downs and an up make a neutron. Quarks always come grouped together to make bigger particles, and the only stable ones are the proton and the neutron. And in fact, even the neutron isn't stable unless it's in an atom. So the only stable ones are the proton and the neutron, so that means we're basically dealing with up and down quarks all the time, and electrons, and that's what makes up atoms. Well, there's another particle you deal with absolutely all the time, and that is the photon. The photon is the particle of light. So whenever you're seeing anything, there is light going on. And okay, so that's great. Those are the ones you deal with, but it turns out there's a whole bunch of other particles, including here the electron neutrino and its antiparticle. So one thing I've left out, there's an antimatter partner to each one of these. So the electron, there's also an anti-electron, also called the positron. For a down, there's also, well, we usually just call it the D bars because we draw a bar over the thing to call it an antiparticle. So there's a D bar and a U bar. So there's an anti-down and an anti-up. It's like anti-Mildred, except anti-down doesn't make pi. So there's an anti-down and an anti-up, and there's also an anti-neutrino. You might ask, what is the anti-photon? It turns out that the antiphoton is the photon. The photon is its own antiparticle. So there's no such thing as an antiphoton. Photons and antimatter photons are the same thing. Well, that's great. So these guys we deal with. These we now know to make beta decay work and nuclear fusion work, this, and we deal with this all the time. But that's not all there is. Next, we have these things called gluons. And gluons are, they're what holds the nucleus together, and that's why they're called gluons. And I'm not going to talk a lot about them, but okay, there are things. We know about them. But the interesting thing is that there are these other generations of particles that do exist, and we have seen all of them in particle accelerators now, but they're not part of regular matter in that we don't, all the bigger particles that are made out of these things are unstable and decay in a tiny fraction of a second. Muons, it turns out, are raining down on you at all times. Cosmic rays are high energy particles that go shooting through space, and when they hit our upper atmosphere is really thick compared to space. So when high energy particles hit them, all their energy creates huge numbers of random other particles, including lots and lots of muons, and then the muons kind of rain down. So muons are hitting you right now. Sorry, but it's true. But also some of the muons don't make it to the ground because they don't live very long. Again, they live a tiny fraction of a second and decay to other things. So these things are out there. And when the muons were first observed, I think it was Robbie was the guy who said, there was a famous physicist who said, the muon, who ordered that? It wasn't necessary. It didn't fit in. We could make all our protons and neutrons and all kinds of stuff, including other particles we'd seen, from just the up and the down quark, which we actually didn't even really know about up and down. We just called them protons and neutrons then, and electrons. The muon was seen to be unnecessary, and it behaved like a heavy electron that was unstable. And so nowadays, we know that the muon is in a lot of ways like an electron. It's just a different flavor of electron, sort of. It's much more massive, but it has the same charge as the electron, and lots of other quantum properties are the same, but it is a different particle. And there's also the tauon. And as with the electron, each mu and tau also has a neutrino associated with it. So there's the muon neutrino and the tau neutrino. Each lepton, as it's called, so all these green particles here are leptons. Each lepton has a partner neutrino that goes with it, and an antineutrino as well. So that's what we mean when we talk about flavors of neutrons. There are also other kinds of quarks that make temporary particles that I won't really be talking about here. But what's important is that there are 3 different flavors of neutrons. The electron neutrinos are the ones that are produced in fusion in the sun. Why? Because fusion in the sun produces anti-electrons, and so it's the neutrinos that go with electrons are the ones that get produced. All right, so there are 3 different flavors of electrons. Yes, that's the punchline there, is that neutrinos will change flavors. They don't actually change. Neutrons don't have color by the physics way of talking about it. Yeah, they change flavors mid-flight. So there are 3 different flavors of neutron. Sorry, neutrino. There's only one kind of neutron. Well, okay, here's the thing, though. If you remember that Ray Davis experiment I talked about, the big tank of chlorine, it was only sensitive to electron neutrinos. Why? Because the neutrino that comes in and collides with the chlorine has to be an electron neutrino in order for the reaction that makes argon to go. The other types of neutrinos would not interact with chlorine in order to make an argon nucleus. So that was just measuring the amount of electron neutrinos that came in. So then there's the question, how do we find other kinds of neutrinos? Well, okay. There's a few ways you can do it, and I'm going to use some jargon here called currents. Ugh, why currents? Well, whatever. There's reasons why they call it that, but just accept it as jargon for now. And the reason I'm doing this is so that you'll understand a plot that I show later. They just mean different types of interactions that are sensitive to different types of neutrinos. This thing here called the charged current interaction is a way to detect neutrinos. Now, this D here means a deuteron. A deuteron is like hydrogen but heavier. Hydrogen has just one proton with one electron orbiting it. A deuteron is a heavy hydrogen nucleus that has one proton and one neutron together. The easiest way to find deuterons is to get heavy water. Heavy water has one of the hydrogens in it is in fact deuterium rather than hydrogen, so it has an extra neutron. Well, it turns out that electron neutrinos will interact with a deuteron by converting the neutron into an electron, and 2 protons come flying out and an electron. And if you then measure the rate at which those electrons are coming out in their energy, that's called the charged current because electrons have charge. So that detects just electron neutrinos. However, it turns out it's also possible to blast apart deuterons by taking any old neutrino, and instead of converting the neutron into an electron, you just take the energy of the neutrino and you blast it apart. And you have a proton and then a neutron. And then the proton will probably stay there and hang out and be heavy water. It might go flying as well. It probably will go flying, actually, but might get recaptured. But the neutron will probably fly free, and if you can detect those neutrons, you now have what's called the neutral current. This nu sub x means it works with all 3 kinds of neutrinos. So because we're not converting things, thank you. Who ordered the muon is the classic quote. Because here it has to be the electron neutrino, because we were converting something to a proton and we have to get an electron out. This reaction works with all kinds of neutrinos. And finally, there's another reaction called elastic scattering, and that's just when you have a neutrino bouncing off an electron. Neutrinos will bounce off of electrons, and the electron comes out with higher energy, having been kicked around by the neutrino. So these are 3 different things that you can measure, but what's interesting about these is that this one is sensitive only to electron neutrinos. This is sensitive to all kinds of neutrinos, and then this here is sensitive to all kinds of neutrinos, but with a different energy profile. And here is the complicated plot that I want to spend some time with. First of all, if you look at these little phi's. This is the Greek letter phi. What it really means is flux. It says just what's the rate at which neutrinos are coming in. So there you go. Here's the flux, the rate at which neutrinos are coming in, being detected by the detector. Not really, this isn't the rate they're being detected. I think it's the rate they're coming in. So that's what phi means. So all these things are different phis, and I'll talk about the colors later. The superscript tells you which experiment is doing it. So SNO means the Sudbury Neutrino Observatory. This, without the superscript, I think is from Kamiya Kanda. And then the subscript tells you what kind of thing is elastic scattering, or is it charged current or neutral current. Honestly, I forgot what that is, so I apologize. So you can ignore these dotted lines if you want. Okay, that's great. Now, the horizontal axis tells you the flux of just electron neutrinos in whatever these units are. Don't worry about it. It has to do with number per second per thumbnail. So this has the flux of just electron neutrinos. All right. So this says, here, that just means there's twice as many as if you plot here. The vertical axis is the flux of mu and tau neutrinos together. All right. This actually says subscript alpha tau, but it was supposed to be subscript mu tau, and I don't know what was going on with the titles in their plot. So this horizontal axis is number of electron. This is the number of mu and tau neutrinos. And then what the colored bands are the data we collect in our experiment are consistent with electron and mu tau fluxes being anywhere within this colored band. So the neutron current, which is sensitive to all kinds of neutrinos, can't actually tell, is it an electron or is it something else? It just sort of measures a total flux. So if there's no electron neutrinos, then the flux in these units has to be 5 for the other two. If there's none of the other two, then the flux in electron has to be 5. But it could be anywhere in between on these two things. But the charged current is only sensitive to electron neutrinos. So we're getting something like 1.8, 1.9, something like that. Or no, it's more like 1.8. We get something like 1.8 in these units for electron neutrinos. Here's the interesting thing. The total flux of neutrinos coming from the sun is about 3 times what just the electron flux is. And that 3 is an interesting number because the electron neutrino flux is 1/3 of what we predicted. So if the electron neutrinos produced in the sun could turn into other kinds of neutrinos in between when they were emitted and when they get detected, then the total flux of all 3 kinds of neutrinos would in fact be the total number of neutrinos that were produced as electron neutrinos in the sun. And when we measure the total flux of all 3 kinds of neutrinos, we get the right amount. So this right here is the solution to the solar neutrino problem. It tells us there's something weird about neutrinos. And what that weird thing is that, in fact, neutrinos, electron neutrinos, can turn into mu and tau neutrinos in between when they were produced in the sun and when we detect them. How does a neutrino change its flavor? This isn't something that electrons ever do. An electron never spontaneously turns into a muon. That just doesn't happen. But an electron neutrino can just spontaneously turn into a mu and a tau neutrino. That is weird. And so now we're going to get into some hardcore quantum theory. You ready for that? Everyone duck, because the hardcore quantum theory is coming. All right, quantum properties. I've already talked about quantum properties are quantized, meaning there's only a finite number of quantized possible values. We talked about orbitals and electrons are an example of a quantized quantum property. They're energy levels. Now I'm going to talk about spin, which is just angular momentum. If you look at electrons or neutrinos, either way, but if you look at electrons, let's just start right now, the angular momentum of an electron, the total angular momentum of every electron is exactly the same. If you measure how much is it spinning along, say, the up-down axis? And so that just means like this. Think about this. You could have a ball that's spinning like this. It could also be spinning sort of top to bottom, and then the axis would be horizontal. So there's different directions things can spin in. If you look just along this axis, is it spinning clockwise or counterclockwise? It turns out that it can either be a certain amount clockwise or a certain amount counterclockwise and nothing in between. It's always exactly this or exactly that whenever you measure it. You never get 0. Meaning it can't ever be spinning entirely horizontally, which is kind of weird. but that's standard quantum mechanics, right? So the basic idea is there's these different states that if you measure that state, if I measure the vertical spin, or the z-axis spin, as we say, of the electron, every time I measure it, I either get this state or this state and nothing else. Right? That's what you get. That's quantum mechanics tells you that. Well, it also turns out, though, that before you measure it, the electron can be in a mixture of states. Like, suppose I measured along a different axis. If I measure it along a horizontal axis, I get either plus or minus spin along that axis. The vertical axis at that point is what we call indeterminate. And this is weird quantum mechanics notation. Don't worry about what all the math means, but notice this. I've got this little up arrow inside this. It's called a ket, but inside these sort of weird brackets, and a down arrow, and then 1/1/2. Again, don't worry about the square roots. This is just a quantum mechanical way of saying that an electron is half up and half down. That is different from being zero. Like, half up and half down is not exactly zero. What it means is that if you make the measurement, there's a 50% chance you get up and a 50% chance you get down, but before you make the measurement, it isn't either one or the other. It's in what we call a mixture of states. All right? So this is the Schrödinger's cat thing. The Schrödinger's cat analogy is that if you put a cat in a box together with something where there's a 50% chance of a random process killing the cat. I do not approve of this, by the way. I really do not approve. But it's a thought experiment, so we're going to go on with it. There's a random process where there's a 50% chance of killing the cat. If you wait the right amount of time so that there's exactly a 50% chance, if you don't open the box, not only do you not know if the cat is alive or dead, but if it's a random quantum process, then the cat neither is alive or dead, but is in a mixture of states of aliveness and deadness. And only when you open the box and make the measurement, look at the cat, see if it's alive or dead, does it become either alive or dead. Right? That's a really weird idea, but that's sort of how quantum mechanics works. That particles can be in mixtures of states, but when you measure it, it goes into what we call an eigenstate. So these are the z-spin eigenstates. An eigenstate means a state that you could actually measure. And so the z-spin eigenstates are up and down, but before you measure it, it might be in a mixture of states. So that's what happens with angular momentum. Yes, but here's the thing, is if you're content with a purring box and then the purring stops, then you're nervous and you open the box because you're worried about your poor little kitty. So here's the thing. Give your kitty a box to play with. Do not put poison in the box. Okay? That's what you should really do. Also, this thought experiment wouldn't really work for all kinds of complicated reasons, but there's whole other talks about quantum indeterminacy I could give. Okay, now here's the next thing. I sort of mentioned this already, that y-spin eigenstates are not the same as z-spin eigenstates. What that means is that if you measure the y-spin of an electron and you get that it is plus in the plus y direction, then the z-spin is now in a mixture of states between up and down. So if I then measure the z-spin, I'll have a 50% chance of getting up and a 50% chance of getting down. If I measure y and it's the other way, it's the same thing. This negative sign has to do with complicated math of quantum mechanics, and you don't need to worry about it. The basic idea is that if you know the y-spin of an electron, it's in a y eigenstate because you just measured it and it has a well-known spin, the z-spin has to be indeterminate, and vice versa. If you measure the z eigenstate of an electron and you now know the z-spin, the y-spin becomes indeterminate. Right? So the idea is there's different bases. There's two different ways that you could look at electron spin. You could look at how fast is it spinning around a vertical axis, how fast is it spinning around a horizontal axis. And that if you measure one, it will have a definite state along that, and there's only two definite states. But once you've measured one, the other becomes indefinite. Only one of them can be definite at a time. This is a really, really weird quantum mechanics thing, that there are different ways of looking at things, that only one can be definite at once. And this is deeply related to the Heisenberg uncertainty principle, if you've ever heard of that, which tells you that there has to be certain uncertainty in things. And I'm going to leave it vague like that for now. Well, okay, and there's a whole bunch of thought experiments that I'm going to skip over here because we don't have a lot of time. But here is the bottom line. So, remember this, it is German. In fact, it's German for its own. I think eigen means its own or something in German. So here's the bottom line. So let me just remind you what's going on here. we have electron neutrinos produced. Oh, it's in Dutch too. Good. Okay. We have neutrinos are produced in the sun, and this is actually a different reaction from the one I showed you. This is the first reaction in that chain. Two protons come together, stick to make a deuteron, kick out an anti-electron, and kink out a neutrino. Now, this neutrino has to be an electron neutrino because to balance the fact that an anti-electron was produced, because the total electron number has to stay the same. So since an anti-electron has an electron number of -1, that's part of what makes it anti, you have to have a electron neutrino to balance that out. So in this reaction, it must be an electron neutrino. Great, so we have produced an electron neutrino. But then they fly from the sun to the Earth. And as they fly from this Earth, what really propagates through space, what's really sort of stable in space, is mass eigenstates. Now you say, well, okay, well, so what? Well, all right. So if you look at quantum mechanics and you just take the propagation of a free particle, the thing that propagates naturally and the things that are stable are things that have definite energy. But okay, you can have a particle of different masses can have the same energy just by having different amounts of kinetic energy. But the things that actually propagate are mass eigenstates. So by letting them fly through space, in a sense, what you're doing is making it have a definite mass. Now, I'm brushing all kinds of stuff under the rug, and there's all kinds of things like correlation lengths and decoherence and blah, blah, blah. So those of you who know more about quantum mechanics know that I have a lot of stuff under the rug, but it's a reasonable oversimplification to say that stuff that flies through space has to be at a definite mass. So what that means is, even though it was produced as an electron neutrino, now it has to have a definite mass. Well, okay. But what does that mean? Well, then when we detect neutrino, it has to be of a definite flavor again now, because it is the flavor of the neutrino that is what links it to the other things it's interacting with. So when we detect a neutrino, it's very much like measuring the angular momentum of an electron along the z-axis, right? It now has to have a definite flavor again. Well, all right. There are three different flavors of neutrinos. There's three different kinds of neutrinos: the electron, the muon, and the tauon. There are also three different possible masses for the neutrino. If I go back to my standard model slide, and let's see if I can do this. That doesn't do it. All right, I don't remember how my thing works, so oops. I'm just going to click previous enough times until we find it. There's a way to just jump to a given page, but I forgot. If you look at the standard model slide, and if you really zoom in on it, you'll notice for the electron, the muon, and the tauon, there's this thing that says MeV and GeV at the top. That stands for mega electron volts and giga electron volts. This is the mass, although it's in an energy unit, so we're using E equals mc squared to convert mass to energy. Notice the muon is heavier than the electron, and the tau is heavier than the muon. There are three different masses of leptons. There are three different flavors. The electron flavor has this mass, the mu flavor has this mass, the tau flavor has this mass. Well, next, there are three different flavors of muons, and they are three different masses of muons. So one way of saying that, there's three flavor eigenstates, electron, mu, tau. There are three mass eigenstates, lightest, medium, and heaviest. But the mass eigenstates and the flavor eigenstates are not the same. The same as the eigenstates for an electron spinning up and down are not the same as the eigenstates for an electron spinning left and right. So an electron neutrino is actually a quantum mechanical indeterminate mixture of the three different masses of neutrinos. And the lightest neutrino is a quantum mechanical indeterminate mixture of the three flavors of neutrinos. And so what neutrino oscillations really means is that electrons produced as one flavor then oscillate in a quantum mechanical way, where oscillation makes sense if you know the mathematics of quantum mechanics, because there's sinusoids and such that show up. But really oscillate means they change their flavor because as they fly through space, they're in a definite mass. Which mass? Don't know. They start as an electron. So then one of the masses will propagate based on the probabilities of what that electron neutrino can be. Then when we detect it, well, a neutrino of a given mass will be detected as one of the three flavors based on the probabilities of the flavors. Right? And so that's what neutrino oscillations is. There are three different types of neutrinos, but based on how you look at it, there's either the electron, mu, and tau, or there's lightest, medium, and heaviest. Those different ways of looking at it don't divide the neutrinos exactly the same way. And so the electron neutrino is a quantum mechanical mixture of the three masses. The lightest neutrino is a quantum mechanical mixture of the three flavors. So even though it's electron neutrinos that are produced, by the time they get to the Earth, they will have turned into lightest, medium, or heaviest neutrons. And so then when we detect them, we randomly detect any of the three types of neutrinos. And so that here, oh, I pushed it too many times. I wouldn't say it's, I don't know exactly what you mean by that. So I can't really answer that question, a quasi-stable manifold boundary region. I mean, really, so there is a coherence length. So it really depends on, so people have also done neutrino oscillation experiments looking at neutrinos from nuclear reactors. And those do not oscillate as much because actually they have to fly a good long ways before they really become into a mass eigenstate. So there's all kinds of math of quantum mechanics that goes behind this that's way beyond the level of this talk. But anyway, the basic idea, though, is that neutrinos come in three flavors. They come in three masses, but you can't identify a given mass neutrino with a given flavor neutrino. So if there's a given mass, are the oscillations periodic or random? Well, they're random, really. But what happens is that there's a periodic amplitude term in the quantum mechanical expressions. But once you get far enough away that you're many periods away, it becomes random. So when you're within, say, the first period, it's less random, and you're more likely to detect whatever it was emitted as. But when you get far enough away and you're many periods away, it's no longer coherent. It's sort of like trying to keep waves in phase with each other. If you have two waves that are almost exactly the same frequency, they're almost exactly in phase, meaning when one is going up, the other is going up when you start. But when you get much later, they might be in phase or out of phase or not. And so you think about like sound waves or even ocean waves, they just become more of a mess the further away from the source that you get. So it's the same kind of thing, but it's not what's actually waving is sort of a quantum mechanical probability amplitude, which is a much more abstract thing than the up and down you get with water waves. Yes, it's quantum mechanics is deep and fancy. Decoherent but bounded on specific states. Yeah, you might be able to describe it that way. I think you're using a way of talking about quantum mechanics that I'm not terribly familiar with. So are there any other questions that anybody has? Oh, yes. Actually, Vic does point out a very important thing is that neutrinos must have mass as well. The standard model sort of assumes that neutrinos have no mass. And now neutrinos actually do have mass. And so it wasn't known until 1999, I think, is when this neutrino oscillation discovery was made, that neutrinos have mass. For neutrino oscillations to work, they must have mass, and the three masses can't all be the same as each other. If they were all massless, neutrino oscillations would not work because there would not be different mass eigenstates. So another part of this discovery is that neutrinos must have mass. They can't be massless particles. They are really, 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 really light, meaning that compared to the mass of even the electron, the mass of the electron neutrino is basically zero. But the mass of the electron is 1/2000th the mass of the proton, so the electrons are already light. Electron neutrinos are much lighter than the electron by like at least a factor of 1,000,000. But it's not zero, so they do have some mass, just not zero. Any other questions? Yeah, Baragon, it's not completely unrelated. The neat thing about sensitivity to initial conditions is that happens even in classical physics. So you don't need to have quantum indeterminacy for that to happen. That's a form of unpredictability. So it's not really indeterminacy in the same way. There's something fundamental about quantum indeterminacy that doesn't show up in classical physics. But unpredictability certainly happens in both. And so, yeah, chaos, which works even in classical physics, has extreme sensitivity to initial conditions. And so, yes, chaos can come into quantum mechanics as well. It's just usually we don't think about it because we're too busy trying to understand the indeterminacy of quantum that comes even before chaos comes into it. My theorist, I'd say I'm an experimentalist primarily. Really, I'm an observational astronomer who's turning into a computational astronomer. Those of you who remember MICA or MICA or MICA, depending on what you called it, was the Meta Institute of Computational Astrophysics. It hasn't been around for a few years now, but I was a part of that. And I'm turning into a computational astrophysicist, but I've also been an observational astrophysicist. So I'm really not a hardcore theory. How many neutrinos per regular particle? Okay, so something like that. But most of the neutrinos were actually produced in the Big Bang, and most of them are so low energy that we have almost no hope of detecting them. Although, of course, Pauli said the same thing about neutrinos at all. But these are really, really hard to detect. So there's huge numbers of neutrinos all over the place left over from the Big Bang. And I don't know what the ratio is, but it's probably something like that. So there's lots of neutrinos left over from the Big Bang, and then there's lots and lots and lots of them left over from nuclear reactions. Yeah, so even a tiny bit of mass may have some implications. You might think, wait, what about dark matter? And so the leftover neutrinos from the Big Bang were a real possibility for the dark matter particle. But nowadays, based on, to make everything else work and to be consistent, the total number of neutrinos in the universe and the limits on their mass isn't enough to make up the dark matter. But it wasn't too terribly long ago that this was actually a possibility, that these leftover neutrinos could have been the dark matter. I know it is kind of a bummer, because then it would be sort of a parsimoniousness of explanation would be, hey, this particle we already know about. Turns out there's just more of them, and that's the dark matter. But unfortunately, that doesn't work. No, it's much more like a half-life with a neutron decay. So they don't really change in a fixed time. They change quantum mechanically randomly, and so they have a half-life. It's sort of like a half-life for how long they change in flavor. And then, so if you think about it, if you had a whole bunch of neutrons, and so the neutron half-life, I forget, it's something like 10 minutes. If you have a whole bunch of neutrons and you measure again how many neutrons you have a second later, you might not notice that neutron decay even happens because you haven't waited long enough for it to be appreciable. So it's the same thing if you make neutrinos, yes. So if you make neutrinos and you measure them shortly thereafter, they'll still all have the same flavor. But if you wait long enough, then the time scale for neutrino flavor oscillation will be long enough that sort of with neutrons, if you wait 10 minutes, you'll say, hey, half of them are gone. If you wait long enough for the neutrinos, let them fly far enough, then you'll say, hey, wait, half of them have turned into another kind of neutrino. So it's much more analogous to radioactive decay than it is to oscillations on a fixed time scale. It's a probabilistic kind of thing. There's a lot of stuff we don't know. We know a lot, but we also know that we don't know a lot. This is different from at the end of the 19th century. Physicists in general thought that we basically almost knew everything, that we had good theories that worked, that explained all the realms. We had Newton's classical mechanics, described how particles moved around. We had statistical mechanics that worked really well for huge numbers of particles. And then we had electromagnetic theory, which was this extremely successful theory that unified electricity and magnetism and described light as electromagnetic waves. And it was all great. We had explained all the observations we had, except for a few little outstanding things, but we just figured, oh, we'll figure out what's going wrong with the calculation or something. There'll be a little tune-up that we can make. It turns out to fix the little outstanding things required completely and totally revolutionizing our idea of reality by introducing relativity and quantum mechanics. And so we were nowhere close to understanding everything back around 1900 or 1890, thereabouts. Well, so physicists today, we all believe that the standard model is a good explanation of things, but we're much more cautious, and we describe things as models. Our theories are models. They're good approximations that work really well, but we know there's deeper stuff going on because there are a few things that we can't really fully explain yet. Like exactly why do neutrinos have mass? Why does it look like the expansion of the universe is accelerating? Why does it look like there needs to be dark matter that's a particle we haven't identified to make all kinds of different stuff work right? and astronomy. So we know there's lots of questions out there, and that's part of what makes it fun. So we can explain a lot more than people could explain 100 years ago, but we also have found a bunch of stuff that we still can't fully explain. All right, well, thank you all for coming. I'm going to head out now and probably have some lunch, because it's time for that sort of thing. So thank you all for coming. I'm going to give another talk in a few weeks. If you've heard of the WTF star, which stands for Where's the Flux, not what you thought it stood for. That was a star where people were briefly invoking aliens to explain. Nobody does anymore, but I will talk about that star in a couple of weeks. So thank you all for coming. Tell your friends about the other talk, and hopefully I'll figure out what the URL is, and you can find this on YouTube later. All right. Have fun, everybody. Oh, and I'm going to make this slideshow so that anybody can copy it if it's not already. If you want to get a copy of it, you'll be allowed. Assuming I can find permissions. Anyone can copy. Oop. There. I've set it so anyone can copy, so feel free to steal a copy of the slideshow if you want. All right. See y'all later.